All right, so in this set of notes, we are going to go over the basic limit laws that allow us to evaluate, I don't want to say composition because it's not a composition of limits, but it could be like the addition, multiplication, sum of limits. The same way that we have all of these operators that we can do with functions, we can do them with limits as well. Some of them might just be a little particular. So the two most important limit laws that you need to know, the limit of a constant and the limit of a single variable, like a plain X or a plain Y. No powers on it, no coefficients. So if I'm looking at the limit of a constant, let's say X is approaching 5 and I'm evaluating the limit of 12. Constant functions are just horizontal lines. So no matter what X value you are approaching, all of the Y values are still going to be 12 or approaching 12. So the limit of a constant, no matter what X value you're approaching, is just the constant itself. And then the limit of X or Y or M or Z or star, it does not matter, is going to be whatever the X, Y, Z value is approaching. So basically, it's kind of like I'm passing the X value that we're approaching into X, and that would be the value that it is. And that's why I said it has to be just a plain X, no power on it, no coefficient. You're basically just allowed to evaluate that plain X function at that C value, which hopefully should make sense because we're basically looking at evaluating the function Y equals X. And we all know what that looks like. So those are the two most important ones that you will be using all the time. Now I'm going to go into the other basic limit laws. Like I said before, this is just your basic like adding of limits, multiplying function, or multiplying limits, multiplying a limit by a scalar, so on and so forth. So in order to use these, the limits themselves must originally exist. So if I'm looking at the limit of two functions being added together as X approaches C, that would be the same as the limit of each function individually being added together. So I could separate them like that, or I can put them together. Excuse me. If I'm taking the limit of a function being multiplied by a scalar, so if I'm looking at, let's do an exponential function. That might be easier to think about. 2 times 5 to, or let me choose a different number, 7 to the X. What if I just want to do 7 to the X? I could bring that 2 in front and evaluate the limit of 7 to the X as X approaches 5. Or kind of just bringing it back to one of those basic limit laws, maybe I'm doing the limit as X approaches 5 of 2 times plain old X. Well, hey, I know the limit of plain old X can just be whatever the X value is that we're approaching. So I can bring that 2 out front. 2 limit as X approaches 5 of X. Bring in my 2 times, I know the value of that limit would be the X value that we're approaching. So then I can get 10. This is breaking limits down into a ridiculously like simple level, one that honestly we don't really need to use, but I would like you to feel comfortable using the limit laws and breaking things up that small for now. Kind of like once you master something, then you get to break some rules. Not that you're rule breaking. Moving on. All right, so next one, if we are multiplying two functions inside of a limit, I can multiply their limits individually together. Then we have our quotient. If we are taking the limit of two functions being divided, I can divide the limits of those functions individually. But there's a caveat to this. You can only break it up if the limit of the lower function does not equal 0. If it equals 0, sorry, you cannot break it up. And we will actually be looking at some examples of this. So just be prepared. If you want to break limits up that way, you have to double check. Does that denominator limit equal 0? If so, sorry, you cannot use this technique. And then the last one, if we have, sorry about that, guys. If we have a function raised to a power, we can actually take that power outside of the limit, evaluate the function as is, and then apply the power to the result. Now, all of these have names. So I'm going to write them down. I would like you to as well. They should make a lot of sense though. We have sum, limit law. We have a constant multiple, or you can say scalar. Product. Quotient. And write that note that you can only split it up this way if the limit of your lower function does not equal 0. And then we have power / roots. All right, so let's get into our first example. It says state which limit laws can be used to evaluate this limit. So I would like us to break this up into the most basic, important limits that we have up top. I'd like us to break it up into limits of constants and limits of just plain old x's. That is the only thing I want to see in there. All right, so I would like you to try to work through that, and in the order that you are breaking these up, I want you to write that down in the Edulastic. See you back in a few. All right, so this is what I got. I would do product first because I see that these factors are connected through a multiple or through multiplication here, so I can separate them using product. Now, looking at the example, I know that I curated it, but at the same time, if this were a problem in the textbook, I would be shocked that the next move that I could do on both of these is actually the same. I wouldn't have expected that, but I can actually apply the power / root limit law to both of these at the same time, since both factors have powers applied to the entire expression. All right, so this first one's actually looking done. I have a limit of that single variable, no powers, no coefficients, as t approaches 3. So the first one's done. Now, this second one is going to need broken up a little bit more because I have both a t and a +5 on the inside. So I'm going to break those up into their own individual limits using that. Which one is it? Sum limit law. Putting them in their own limits. I now have it broken up into limits of my single variables and then my limit of a constant. So I can go ahead and evaluate all these. But let me just double check the question even wanted me to do that in the first place. No, it just said state which limit laws can be used. So you don't have to. I will put the answer up here if you would like to try to evaluate these, but not necessary. All right, so aside from rationalizing, this is as far as I could take it. Now, if you do rationalize, just keep in mind that this is a fourth root, so you would have to multiply by an additional 3 square root of 3's. That way you can actually cancel out the fourth root. Like that, top and bottom, but I'm not going to rationalize because this wasn't even part of the question in the first place. All right, let's move on to the next example. Evaluate the limit of 14 as x approaches 3. Go ahead, what is it? Limit of a constant is itself. Example 3, can the quotient law be applied to evaluate that limit? Yes or no? Hopefully you said no. You cannot use the quotient law to evaluate that limit because the limit of the denominator equals 0, and we can't have that. Remember, in order to use the quotient limit law, the denominator limit cannot equal 0. So the next question we have is, well, does that limit even exist in the first place? Let's take a look at the graph. I'll put that in your graphing calculator and mine will pop here in just a second. For those of you with the newer calculators, if you do alpha x, you can get a fraction to pop up. And you can also see my key history here at the bottom of the screen. I personally own one calculator that does this and one calculator that doesn't. So if you can't, then that's fine. Just make sure that whenever you're doing rational functions, you're typing them into your calculator appropriately. These are just single terms that we're typing in here, sine of x over x. So we don't need to worry about wrapping the numerator in parentheses or the denominator. So we're good with this. But we do need to make sure that we are in the correct mode since we're dealing with trig functions. We need to be in radian mode when we are in calculus, which I usually am, except when I am teaching geometry. Sometimes it does have to switch back and forth. All right, so let's take a look at the graph. I'm going to do zoom standard, so zoom 6. All right, so it does look like the limit exists as we approach 0 from the left and from the right. I'm going to zoom in a little bit closer just to see, like, am I just out too far? Is there some crazy like oscillations happening there? So zoom in. And then do you guys see how there's that cursor blinking in the middle of the screen? I'm going to scroll up to where the part of the graph looks like it's going to be 0 and press enter. Okay, so it does look like the limit exists. It looks like we're approaching 1 from either side of 0. I just can't plug 0 in. There's not going to be a value there, which we can even double check by looking at our table. Yeah, no value is going to work there. So yes, visually / graphically. Alrighty. We will actually learn how to evaluate this type of limit eventually using a different type of limit evaluating technique. But for now, we are just going to have to determine this limit graphically. That's all the skills that we have to do that for now. If you have any questions, make sure that you ask them in class.